Hey everybody, this is Mr. Piercy, and what we're going to be taking a look at in this video is what's known as the second derivative test in calculus. This is piggybacking off of what the first derivative test was, which allowed us to identify where mins and maxes were on a given function based off of whatever the critical numbers of the derivative were. Well, we're going to be doing similar things with the second derivative test. Obviously, we'll be taking the second derivative of a given function. But what the second derivative test is going to allow us to make conclusions on is whether the function is going to be concave up or concave down. So what we're seeing here in the first diagram on the left where it says concave up, essentially what that means is that whenever the function itself is going to be concave up, the second derivative of whatever your function is going to be greater than 0. It's going to be some positive number, and consequently, if the function itself is concave down, then the second derivative of whatever your function is going to be less than 0. And if you wind up at an inflection point of some kind, then the second derivative of the function would be equal to 0 at that point. So how do we apply this here? What we're going to be taking a look at first here is to just see how the slopes of the functions are going to be changing. So what it's telling you to do, and I've kind of already had it here for you, it says draw small tangent lines along the curve to see, well, what do you notice? And the one on the left, when it's concave up, the slopes are changing from being in decreasing slope to be in an increasing slope, and vice versa with the concave down function that we have on the right. Then the slopes are changing from increasing to decreasing, obviously, as we go from left to right. Now, what we're looking at here is a table in your notes where we're kind of looking to say, okay, well, what are some conclusions that we can make when we know what the value of the second derivative is, whether it's positive or negative or 0. And here, this is kind of what we're looking at. I would look at it in columns from left to right, where the first column says that if the second derivative is positive and the first derivative is positive, then the function is going to behave in an increasing manner and it's going to be concave up. However, if the second derivative changes to being negative, but the first derivative is still positive, the function will still be increasing, however, it will be in a concave down format. And if the second derivative is 0 while the first derivative is positive, that's basically going to tell you that you're going to have an increasing function, but there's going to be an inflection point somewhere, kind of like the cube root function. The middle one, obviously, if first derivative is negative, but the second derivative is positive, that's going to give you a decreasing function that will be concave up. The next one, decreasing concave down, when both second and first derivatives are negative. And if the first derivative is negative, but the second derivative is 0, then we're going to have a decreasing function with an inflection point, kind of like if we took the cube root function and reflected it horizontally. And the last column, if the first derivative is 0 and the second derivative is positive, that indicates that you'll have a minimum value somewhere, so your function will be concave up. Next one, with negative second derivative, you'll have a relative minimum, and that'll be concave down. And I think that's supposed to say maximum. I think that's a typo here. This is supposed to say maximum instead of minimum. And finally, if both the first and second derivatives are 0, then that basically just tells you that the function is going to be smooth and level, and that there's possibly an inflection point there that we need to identify. So moving on. Here we're given a function, 1/3 x cubed minus x, and we're asked to determine the intervals at which the graph is concave up or concave down. So what we're going to be looking at here really is essentially what we need to do is we need to do a candidate's test for the second derivative of the function. Now, I'm going to walk us through the first derivative stuff, even though it's not strictly necessary. I'm going to go ahead and walk through it here because that'll give us an idea of what the function should be looking like. So I'm going to identify the critical numbers of the given function. So the first derivative in this case will be x squared minus 1, and when I set that equal to 0, either using the difference of two squares or square roots, we can see that I'm going to have two critical numbers when x is equal to a positive 1 and a negative 1. And looking at the candidate's test for this, for the derivative, for the first derivative, we can see that to the left of negative 1, the function is increasing. To the right of negative 1, the function is decreasing. And again, after we go to the right of positive 1, the function is increasing again, where we have roots on the derivative at 0, which would indicate a minimum or a maximum on our function. And so that kind of lets us know kind of what the shape of the function is going to be looking like. Because we're going to be increasing here on this interval, we're going to be decreasing here on this interval, and then we're going to be increasing again here. So and it's pretty typical for a third degree polynomial. You expect it to have some kind of a waveform like that, where we have a maximum at one point and a minimum at another. So that is what I can gather from the first derivative candidates test. Well, now what I'm going to do is I'm going to identify the second derivative of the function that was given to us, and I want to know what the critical numbers of the second derivative are, because that's where the candidates test will be used to show that the function is either concave up or concave down. So here the second derivative is 2x, and solving for x we get x is equal to 0. And when I do the candidates test here, on to the left of 0, it's going to give me a negative value, and to the right of 0, it's going to give me a positive value. So that lets me know when the second derivative is going to be negative, the function will be concave down, and when it's positive, the function will be concave up. So here, these are just my candidates tests for the sign charts that we're looking at, and so here are the intervals at which the function is going to be concave down or concave up. And that's essentially what we're being asked to identify in the question, is that last bit on what intervals is a function going to be concave up or concave down. Here, what we're looking at on this page, this is essentially the two graphs that we would have gotten for the primary and the derivative. So we see the 1/3 x to the third power minus x function is that third degree polynomial, and that's very much kind of matching what the derivative test, or what the candidates test of the first derivative told us. And where the function is negative, so here the second derivative where it's negative, meaning it's decreasing, you can see that on that interval from negative infinity to 0, it is concave down, but after to the right of 0, the second derivative shows that it's increasing, giving us positive numbers, and that's where the function is going to be concave up. Here we're going to be taking a look at a little bit of stuff on points of inflection. These are basically kinds of things that you're going to be looking at where the function is going to have some kind of a tangent line where the function switches from being either concave up or concave down. So go ahead and write these down into your notes as you see fit. As far as, on the left, the first derivative is going to be positive, and the second derivative being equal to 0 is going to give us something along these lines, whereas the one in the middle, when the second derivative is 0, we have this kind of inflection point here, and this is another example where in this case, we have a vertical tangent line to the inflection point, meaning that the second derivative doesn't exist. So here, this third example, what we're going to be taking a look at is, can you determine any points of inflection and discuss what their concavity is going to be? Well, if we want to determine any points of inflection, that's going to show when the second derivative is equal to 0. So we have to get to that second derivative in order to be able to see where those points of inflection are going to be located on the x-axis. Now, it is kind of giving us the steps here to do the first derivative, so we'll go ahead and take a look at the first derivative, giving us 4x cubed minus 12x squared, and we can factor that with a 4x squared and set each factor equal to 0 and solve. And so we're going to get x is equal to 0 with a multiplicity of 2, and x is equal to 3 for the critical numbers of the second derivative. That's where we're going to have some positive or negative, some maximum or minimum on the x-axis at those points of our function. Well, if we're checking to see for concavity, we really need to see the second derivative. So I'm going to take the second derivative of the function, which will be 12x squared minus 24x, and again I'm going to factor out a 12x from the function and set it equal to 0, and then set each factor to 12x is going to be set equal to 0, and then x minus 2 is set equal to 0. And solving each separate factor, we get a solution of 0 and 2. So the 0 and 2, those are the critical numbers for the candidates test for concavity, for the second derivative test. So these are the numbers here. Whoops. There we go. The 0 and the 2, those are the numbers I was really looking for. The 0 and the 2, I thought I had them on top, but I guess I put them on the bottom this time. The 0 and the 2 on that candidates test, that little sign chart that I'm putting together, those are the critical numbers of the second derivative. And so I'm just picking some number to the left of the 0, hence the -1, something in between the 0 and 2, hence the +1, and something to the right of the 2, hence the +3, and we're just plugging them back into the second derivative and seeing what type of outputs are we going to get. So you can see where the second derivative is positive from -infinity up to 0, that tells you that the function is going to be concave up at that point, because that's where the second derivative is positive. It'll also be concave up from the +2 to +infinity, because that's where the second derivative is positive. In between the 0 and the 2, that's where the function is going to be concave down. And because the roots of the second derivative were at 0 and 2, that's where we should have some inflection points in the function. And I certainly encourage you to go ahead and pause the video and try graphing this function on the calculator. Try graphing that fourth degree polynomial and see, do these points match up? Do these solutions that I have here in blue match what the graph is giving you? And ideally, they should be the same. Now here, this next one, this one's going to be a bit of a doozy. This one is really going to rely on some proper trig stuff that you would have seen in pre-cal as far as how you solve a trig equation. And again, this one I'll probably pause at some point so I can put it on a calculator and you can kind of see what's happening here. But here it is telling you to use a calculator, and it says find how many times this particular function, x squared minus 3 plus sine of 2x minus 1, how many times does it change concavity? Now there's one little thing here that I need to kind of mention, because I know right now, the classes that I have right now, we haven't quite talked about the chain rule, even though we've seen it a couple of times in other lessons. And I promise we'll get to the chain rule soon. But here, the sine of 2x minus 1, we're going to have to use the chain rule at this point. And it's really pretty simple. It's the we think of it as a composite function where I have f of g of x. Well, the derivative of that using the chain rule will be the derivative of the whole thing multiplied by the derivative of whatever's on the inside. So we're looking at, when we look at just the sine of 2x minus 1, if I want to take the derivative of that, well, the derivative of sine is cosine. So I have cosine 2x minus 1. That's the derivative of the whole thing. And the derivative of the inside is really where that 2x is. So the derivative of 2x is going to be 2. So I can either say times 2 here, or I can put it in the front and I can say 2 times cosine of 2x minus 1. And so that's how we're going to be taking the derivative of that piece of the function. So this is what we have. We need to find the derivatives, first and second derivatives. So that's what I have here for you, the first and second derivatives. And again, we're using the chain rule again at this point here. We're going to use the chain rule again. The derivative of the whole thing is going to be negative 2 sine of 2x minus 1, and the derivative of the inside is going to be 2, which multiplies to the 2 that's already there, hence the 4 that we have at that point. And now moving on, what we're going to do, since we're looking for changing it in concavity, we want to know what are the critical numbers of the second derivative. So I set the second derivative equation equal to 0, and I am going to attempt to solve it. So I'm going to move the 2 away from the stuff on the right side, then I'm going to divide by the negative 4, and I'm going to get 1/2 to be equal to sine of 2x minus 1. Now this is where we can start seeing, okay, well, where is sine going to be 1/2 on my unit circle? And that is going to be at pi over 6 and 5 pi over 6. So this is how I'm going to set up my equations, because essentially what we're doing is we're going to take the inverse sign of that expression, so that way we can get the 2x minus 1 out of the parentheses. Now what I'm doing is I'm showing you on the left side of the equation where I'm saying 2 pi n plus pi over 6. And sometimes, depending on maybe the curriculum that you used or the teacher that you had for pre-cal when you did trig equations, maybe where I have an n, maybe it was a k, where it said 2 pi k. The n and the k, or whatever that variable is on the 2 pi, that's just representing the number of terms or the number of times that you could have something as a solution, because understand that the trig functions are periodic. So n or k, that's just going to represent some kind of an integer value that we would use to say, okay, well, how many times along some interval where it's going through complete cycles am I going to be able to have a solution at a certain point? So we're trying to solve for x, so move the 1 over and then divide by the 2. And well, here, before I divide it by the 2, I'm just kind of putting everything in a common denominator. And then I'm going to divide by 2 somewhere. There it is. I knew I had it. So we're going to get 12 pi n plus pi plus 6 over 12, and that's going to be equal to x. Now that's for just the pi over 6. I have to repeat the process for the other point on the unit circle where sine is going to be 1/2, and that would be 5 pi over 6. And so here I'm just kind of telling you, this is what you would have seen ideally in a pre-cal class. N can be any integer. In this case, we can only use the integers of 0 and 1, because anything larger than that is going to be outside of the interval that was given to us. So anyway, so we're going to solve this one the same way that we did the pi over 6 expression. Move the 1 over through addition, get a common denominator to simplify things a little bit, and divide by the 2, and I get, in this case, 12 pi n plus 5 pi plus 6, all of it over 12, and those are the expressions that we are going to use to figure out, well, what are the x values that we're going to have there. So if I substitute a 0 in for the n value, or a 1 in for the integer n value, the two answers that my calculator spit out was a 0.762 and a 3.903. And then you do the same thing for the expression on the right, plugging in the 0 and the the 0 and the 1 for the n variable. And we get 1.809 and 4.951. Now, are those 4 decimal numbers inside of the inside of the interval that we're allowed to work in, and in this case, they are. So this is going to show us that the function is going to change concavity 4 different times at those values when x is 0.762, 1.809, 3.903, and 4.951. And here at this point, I'm going to go ahead and pause the video for a second so I can put this stuff into my calculator and kind of demonstrate what I would be looking at on the graph of the calculator. So give me 1 second to get that set up, and then I'll start the recording again. So okay, so it took me some playing around with the Inspire calculator that I have on the computer here, and the function that you have in blue, you can see that was the given function. And what we're trying to determine is how many times does it change concavity. Now, just looking at the function itself is really not all that simple to tell where it's changing concavity. But the 4 values that we got from our arithmetic is we got a 0.762. Now I'm rounding it, obviously. I truncated the number when I entered the 0.762 number here. But you can kind of see that in the table it's showing you that that's where the second derivative, the function that's in black, is 0. And you can kind of see that it looks like on this blue function it's very faint, but it does look like it's concave up along that interval, and then it switches concavity. And so the next point that it should switch concavity at would be at about, what was the next one? 1.809. So let's put that one in there, 1.809. And that's, again, not exactly 0, but it's pretty close to it. And you can kind of see right about here, that's where the number is. And so from here to about here, you can kind of see on that blue curve that it's very faintly concave down, and then it's going to change again to concave up here. And the third point, let's go ahead and look at the third point, see what that looks like. So we're at, maybe I didn't get it right, 1.809. Yeah, it's still showing me that same number. All right, let's try the next x value that we got, which was 3.903. So 3.903. Oh, and I'm not looking at this is the first derivative column. That's why it looks so weird. This is the second derivative column. There we go. So again, you can see it's very close to 0, so about 3.903. So that's right about here, and you can kind of, I'd have to change the scale on my x-axis or on my y-axis here to see where it's moving. But let me see if I can change that real quick, because on our given function, the output at that point, let me escape, we're at about a 12, almost a 13, and I'm not nearly that high up. So let's just, let's change our window settings here a little bit. Window, so the y value, let's raise the maximum to about, I don't know, 25. And so now at about 3.9, where it's, right about here on the x-axis, if you follow it up, it looks like it's going to, be concave down here, and then it very faintly changes and becomes concave up again. So that's really not the easiest graph to see where you're having concavity change, but it definitely is occurring at all 4 of those x values that we identified. And again, like I said, that was a very challenging problem because it requires a lot of prior knowledge on things that you did in pre-cal and solving the equations with the intervals being cyclical, and that was not a very easy to answer question, but we can do it. I'm sure we can do it. All right. So now this next one, example 5, again, it's going to ask you to use a calculator and kind of, again, where is it going to change concavity at? So we're going to have to work through the function using the product rule a couple of times here to get to the second derivative. So we want to get to the second derivative. So here's the first derivative based off of the product rule that we would employ to get to the first derivative. And for the second derivative, I'm going to have to use the product rule twice, and I'm going to wind up with this. Now, we don't really need the parentheses, and we can kind of start combining some like terms that we have. And when we're done, this is what my final simplified second derivative is going to be, where I have e to the x power times x squared plus 4x plus 2. Now, what we're trying to do, excuse me, is we need to know what are the critical numbers of the second derivative. So essentially we have two factors. We have e to the x and we have the quadratic in parentheses. Well, e to the x, if we set that equal to 0, that's simply not possible. It's an exponential function. It's not possible for it to have an output of 0, so let's look at the quadratic. Now, the quadratic itself isn't a nice number. If you look at the discriminant, it's not going to be a factorable function. So I'm just using the quadratic formula to identify, well, what are the roots of that quadratic, so that way I can have my critical numbers. In that case, I get a -2 plus or minus the square root of 2 when I simplify everything. So those are the critical numbers of the derivative. And when I look at it here, I don't think I meant to put that one up here yet. This is essentially what the graph of the function looks like. It's not super pretty, but the -2 plus or minus radical 2, those are the decimal numbers that we're seeing in the concavity or in the intervals that I have there. And again, I'm going to pause the video and see if I can get a better looking function on the calculator, so just bear with me for a second. Okay, so here is the functions. The blue one is the given function, and the one in black is the derivative. So one of the values that we got from the critical numbers of the second derivative was about this -3.414. Let me see if I can type that in a little bit more clearly now that I'm thinking about it. Let me try going to the table, and let's try -2 minus the square root of 2. Oh, how am I getting a non-real number here? Hold on a second, let me play around with it again. Okay, so sorry for having to keep pausing the video, but I'm not super fast with the Inspire yet. Most of my experience is with the TI-84, but here, if I look at the table settings, so the numbers that we had, the positive, negative, or -2 plus minus square root of 2, where we got the -3.414 and the -0.586. Tried typing them in here, and the calculator didn't want to work with me very well, so I saved those numbers. So this is the -2 minus square root of 2, and you can see that it's giving us a little bit more thorough number here. And if I look at the second derivative, which is what I'm looking for, I get exactly 0, no approximation. So we come out here, -1, -2, -3, about -3.4, and you can kind of see that right here the function is kind of concave up. And at that point, it very clearly becomes concave down. And where does it change concavity? And it should go right about here, where that second derivative is also equal to 0. And that is the second number that I saved, where I had negative 2 plus the square root of 2. So I had that number saved in here. And again, you can kind of see on the second derivative, that's where we're going to be equal to 0, or we should. Negative 0.586, that's what we're looking at here, but the second derivative should be 0. I'm not sure what I'm doing on the calculator wrong, but you can kind of see right here about that root on the second derivative is where on the blue function it changes again. We have a slight inflection point where the function causes it to curve and go concave up again for all of this whole interval from about that negative 0.6 almost to positive infinity. So those are the two places where we're going to be looking at identifying where the function is going to change concavity at the critical numbers of the second derivative. So like I said, I know that these last two examples were a little bit heavy on the algebra, a little bit, a lot of trig stuff that we had to be able to remember, but it is part of the course, so we need to make sure that we know how to do it. Here, I think I'm going to go ahead and have you guys pause the video, and I want you to try and work this one out. Use the second derivative test to determine the relative extrema for this fifth degree polynomial. So go ahead and pause the video and work it out and see what you come up with, and when you're done, hit play so you can check yourself with mine. Okay, so here's the work, hopefully, that you were able to come up with as far as here where it's asking you to identify the critical numbers, because it is asking you to identify the relative extremas, and those are going to come from the critical numbers of the first derivative. And we're able to identify where I'm going to have mins and maxes based on what I have for the second derivative. So here are the critical numbers for the second derivative. The radical 2 over 2, that's going to be about 0.707, positive and negative, on the as a decimal number on your calculator. So what it tells you here, find the sign of the second derivative for each critical number, meaning that, you know, if I take the critical numbers of the first derivative and I plug them into the second derivative and see what do I get. So when at f of 0 I get a 0, at f of 1 I get a 2, and at negative 1, I'm sorry, we're not plugging them into the second derivative, we're plugging them into the primary function, my apologies, and these are the numbers that we're getting, 0, positive 2, and negative 2. So based off of the fact that I'm substituting those critical numbers of the first derivative into the primary function, these are letting me know where I'm going to have my mins and maxes. And because the signs of the second derivative are 0, positive, and negative, respectively, that tells me that here at 0 I should have some kind of an inflection point. Here, because the second derivative is positive, the function should be concave up. And the third one, when x is negative 1, the second derivative is concave down. That means we should have a maximum. Wait, concave down. Yes, concave down. That means we should have a, I think I might have those backwards. Concave up, concave down. I don't think, yeah, concave up. Those are right. But, these are the points that we would have gotten. I don't know, I just got myself distracted a little bit, I think. So the critical points that we got from the first derivative and plugging them into the primary function tells us where our mins and maxes are going to be. So when x was 0, y was 0. When x was a positive 1, we got a positive 2, so there's our relative maximum there. And for at negative 1, when x is negative 1, we got a negative 2 for my output, and so that shows me that I should have a relative minimum there. Now, what we're looking at here, this is the actual function itself and its second derivative. So let me turn the table off here. So what we were showing you is that from negative 1 to about 0.707 negative, that's where this value is, the black line here, that's the second derivative. That is where the function changes concavity, showing you that we have our minimum here where the function is concave up at -1, -2. When at 0, when x is 0, that's where we had our point of inflection. So from negative infinity up to about negative 0.707, the function is concave up. From about 0.707 to 0, the function is concave down. Then it changes to being concave up again from about 0.707 from 0 to about 0.707, so it's concave up along this interval here, and at about 0.707 positive, which is right here for the second derivative where it's touching the x-axis, the function again is concave down, giving me a maximum value at that case when x was 1, y was 2. So that's what we're looking at to identify here. And I believe the next one is a graphing problem, yes. Here, the graph of the derivative of a function is shown. Find where the function is concave up and where it is concave down. Well, this is going to be pretty easy because depending on what you want to do with since they're giving you the first derivative, you can very easily take what you know about properties of the graphs of functions and their derivatives to be able to identify what the primary function would be or what its derivative would be. So what I'm going to be looking at here is I want to go ahead and see, well, what's the second derivative going to look like? So I can treat this first derivative that was given to me, I can just treat it like a normal function and use my understanding of functions and their derivatives to graph the derivative of this, which would happen to be the second derivative. So the function is decreasing from negative infinity up until it looks like about -1, and then it's increasing, so that means my function should be, my derivative should be below the x-axis along that interval, so it should be kind of coming up this way some. And between -1 and about +3, it looks like it's increasing, so that's where I'm going to be above the x-axis. And my derivative, my function has a root here, so its derivative, that's where it should have a maximum. And that's kind of what I'm looking at here. This is, and it makes sense if this is a third-degree polynomial, the derivative that was given to us. So its derivative would be a second-degree polynomial that looks like this, because you can tell by the end behaviors that the leading coefficient is negative, so this parabola has to open down. And what I'm going to be looking at is, okay, well, what do I know about the derivative? So the second derivative is going to be negative on the interval from negative infinity up to about that 1. So that's where my function itself is going to be concave down, concave down. The second derivative is positive between +1 and about +3, so that's where my function would be concave up. And then it goes back negative on +3 to positive infinity, so on that interval the function is going to be concave down. So looking at what I have, I should have function, or because the roots of the second derivative are at +1 and at +3, -1 and +3, that should match where I would have inflection points on the primary function. And these are the intervals that we would be looking at for our conclusion based on about what we know for the second derivative. It's not asking us to sketch it, but we could, if we wanted to, we could probably sketch that primary function, and it should all match what this candidates test is doing and the intervals that we are able to determine where they're concave up and concave down. And that takes care of this particular lesson. This is where we're looking at the second derivative test to identify when the function is going to be concave up, concave down, or have a point of inflection depending on what the critical numbers of the second derivative were. Hopefully you got some good information from it, guys, and if not, by all means, feel free to contact me and get in touch with me, and I'll be happy to help you out. But until next time, guys, thanks for watching. Take care, stay safe, and we'll see you in class soon.